Welcome to Frontline Systems webinar on an overview of optimization applications in Excel using our advanced products. My name is Dr. Sima Maliki. I am Consulting Lead and Modeling Specialist at Frontline Solver. During this presentation, if you have any questions or comments, please type them into the chat box to be answered at the end as time allows. I strive to remain within the promised time frame, yet to thoroughly cover all the material, sometimes it takes a few minutes longer. I very much appreciate your cooperation. As we all know, the optimization applications are widely used across many industries and functional areas. These are just some of the examples: energy and utilities, chemical, manufacturing, agriculture, marketing and sales, so on. We would like you to know that many of our customers have found optimal solutions for their large-scale industrial problems worth millions in savings, as building a model can give you insights and a money-saving optimal solution. Today, we explore how optimization can benefit you in solving your business problems and how easy it is to use our tools to solve them. Together, we'll review typical applications in transportation, inventory management, financial services, scheduling staff, and one example of automating optimization using VBA. Maybe you wonder what solvers are good for. So let's start talking about the decision-making process and using optimization to solve a problem. It is always best and most powerful to efficiently allocate scarce resources arising in your business. It can be your money, equipment, staff time, transportation fleet, or raw materials inventory. All of these are resources and they are allocated for some purpose. Deciding on which products to ship from factories to warehouses along each route is an allocation of products to routes. Portfolio optimization is allocating money to stocks in a portfolio. And scheduling is really a matter of allocating people to time slots or scheduling the availability of hospital operating rooms. Solvers or optimizers are software tools that help you determine the best way to allocate those resources. You might be wondering what you need to do to use a solver or how to define your optimization model. Let's drill down on this further. There are three main steps. They are determining your decision variables, objective function, and constraints. Each optimization problem involves one or more decisions that must be made in order to solve the problem. The decision variables are typically numbers, reflecting how much of some scarce resource is being allocated to some use or purpose, and that is normally under your control. These decisions need to be made in the best possible way while simultaneously satisfying a number of logical conditions or constraints. Constraints reflect the physical situations. For example, some of the constraints represent limits on available resources such as your inventory or money. There are constraints that reflect physical situation. One of them is non-negativity on variables. You cannot produce a negative number of products. You cannot assign a negative number of people to tasks. And some constraints are determined by policies that you or your organization may set. For example, in a portfolio optimization, you might have a limit on the maximum percentage of funds to be invested in any one stock or one industry group. And then you might have balance constraints. For example, warehouses are temporary holding points. Therefore, flow out from one warehouse is equal to its flow in. They have an equality form, or the beginning inventory of this cycle equals the ending inventory of last cycle. Another common element in each optimization problem is the existence of some goal or objective that the decision maker considers when deciding which course of action is best. You can determine the objective function by asking what measures are we trying to optimize. The best or optimal solution might mean maximizing profits, minimizing costs, or achieving the best possible quality. Now it is time to dive in and see how we can solve a problem in practice. Now we are going to look at an advanced example. The goal here is simply for you to see different components of an optimization problem, the decision variables, objective function, or various types of constraints that one needs to consider in a typical real-world application. So please don't concern yourself with details. I will point you to where you can find the examples that we are going to review today by the end of the webinar. Transportation logistic operations of your company can be a competitive differentiator. So in this example, let's find out how optimization can be used to optimize a typical transportation operation. This is about a company that has 3 different goods that have to be shipped from 2 factories to 4 warehouses, and from those warehouses to 5 customers, or directly from factories to the customers with minimum cost. Here you can see a diagram of the system with nodes for factories, warehouses, and customers. Now, we need to show the supply-demand curves displaying feasible routes for the shipment plan. These gold color arrows show the potential flows from factories to warehouses and customers. And then these green arrows show the potential flows from warehouses to customers. Each arrow here represents a different route. What needs to be decided is how much product to send on each route, meaning it is under your control. Let's take a look at Excel workbook. Let me increase the size. This is the full analytic solver platform ribbon, which includes optimization, simulation, and data mining. Today, we are going to focus on a subset of ASP called Premium Solver Platform. So we can change the product. Anytime you are using a free trial of our software, you can do this. Let me show you how. Just click on Help, Change Product, and now you can see all different levels of our products. Instead of Analytic Solver Platform, because we're not focusing on simulation and data mining, let's choose Premium Solver Platform and click OK. Now Premium Solver Platform loads and we only have access to optimization. Let's skim through the Premium Solver Platform ribbon together before reviewing the example, as we will be using the ribbon. You can see that clicking on this Model tab displays or hides the task pane on the right side. In the Model drop-down, there are additional options for multidimensional modeling that you can refer to user guide if you're interested to learn more about them. Optimization Model tab allows you to set up optimization models including decisions, constraints, and your objective function. Parameter tab provides the options to run multiple parameterized optimizations. Solve Action tab allows you to solve your optimization models. Create App feature allows you to convert your Excel models to a web or mobile analytics app with Rayzon. We can run the model 3 different ways. Locally on this machine using the Rayzon IDE, on the web through our developer portal at rayzon.com, or um, in a browser, in a standalone web page that is self-contained, which can be the basis of a web or mobile app. Here on the Analysis tab, you can analyze the results, create reports, and charts. Then you have the Tools tab. Here you can load or save your model in different formats. And then you have the Publish button, allowing you to publish your model for use and distribution on the web. You can use our analytics tools for web spreadsheets. This includes the Solver app for Excel Online and also Google Sheets. Get data. Get data allows you to summarize from big data. You can bring in your input parameter data that you would use to drive an optimization model. For example, if you have millions and millions of sales orders in a large database across different hard disks, you are not going to use every single order in your optimization model. With this facility, you can get a sum or average based on region or gender. Then you have the options, allowing you to set options for your optimization charts and graphs. Now let's explore the Help tab. Here you can display online help, use live chat, control guided mode, which we'll discuss in more details today. Let me actually activate that. Open examples or online tutorials, user guides, and check your license status and more. Now let's review the task bin together. Model tab allows you to view the model in outline form, see the results of model diagnosis, and optionally edit your model elements in place. For example, you can select the constraint and edit its relationship here. Platform tab allows you to view or change the platform options, such as number of optimizations to run or default bounds on your variables. Like if all of your variables have a lower bound of 0, you can set it here, or an upper bound. Next is Engine tab. Here you can select a solver engine and set its option. And then you have the options here. Then we have the Output tab, allowing you to view a log of solution messages or a chart of the objective values. Now back to our example. As you can see in this workbook, the cost of shipping from factories to warehouses, factories to customers directly, and warehouses to customers are recorded in these cells. These are inputs to the problem that are not under our control. For example, these shipping costs are quoted to us by our outsourced shipping company. What is under our control are decisions about how much to ship along each route at these different locations. So we need to reserve cells for variables representing quantity shipped between factories and warehouses and customers. So here we have those cells for factory to warehouses, factories to customers, and also warehouses to customers. So we just reserve cells. This is how we define decision variables. And then you can see in the Model tab, under you can see we have optimization, then we have objective, variables, constraints. In variables, you can see all these 3 blocks are defined as our decision variables. And we are going to practice that together today. So you can see that these 3 sets of variables have name ranges. If you don't know what a name range is, let me quickly show you how we define name ranges. Let's open a blank workbook just to clear that how our tools recognize name ranges. So this is a blank workbook. Now imagine you would like to define A1 through C1 as your decision variables. This is how you define them. You selected those 3 cells and click on decision. This is the easiest way. So you can see it is A1 through C1 defined as variable, normal, and you can see the range here. Now I want to add A2 through C2 and give them a name. For example, I would call them range. Okay, and click enter. So now they have the name range for this row. And then I want to define them as decisions. So I would select those 3 cells and click on decisions. Now you can see that range is added under variables in the task pane. So our products recognize these name ranges and they're helpful to manage your large scale models. So let's go back to our example. That's why we have all these name ranges. It makes it easier to manage this model. What measure are we trying to optimize? Each route of flow incurs a cost. So our objective function is minimization of total cost of shipment along all the routes. You can see it has the name range total cost. If I double click, you can see it is cell C91 and it is defined as minimization. So let's click OK and go to cell C91 and take a look at the formula. As you can see, it is represented by some product functions. Let's look at the first component. To calculate total cost of shipping from factories to warehouses, since the cost coefficient for these routes are defined in cells C10 through F15, we need to multiply these by total amount of product that will be determined to be shipped. Our decision variables for which we have reserved cells C41 through F46. And similarly, we need to add other costs. Now on to our constraints. What restrictions limit our choice of decision variables? The capacity of each warehouse, supplies available from each factory, and the demand from each customer need to be considered. So first one, you can see the warehouse capacity constraints. We need to make sure what we ship into the warehouses doesn't exceed the capacity of those warehouses. We cannot overload warehouses such as each one has a physical capacity. So you can see we have total shipped to warehouses must be less than or equal to warehouse capacity, which are inputs to the model. You can see we have recorded them in rows 50, 51, and 52. We have a certain supply available at each factory provided in cell H63 through H68. The total flow out of factory 1 for each product type must be smaller than or equal to the factory supply. And then this is the same for factory 2 for all product types. And these constraints defined here. Total from factory must be less than or equal to factory capacity. And if you look at the formulas, these are just sums, and we are summing total to factory 1, total shipped out of factory 1 for product type 1. Then we need to ensure that each customer product demand is satisfied. So we have total to customers must be greater than the demand, and demand are inputs, constant inputs to the model. Finally, warehouses are temporary holding points. Therefore, flow out from one warehouse is equal to its flow in this example. These type of constraints, again, are called balance constraints. You can see they have equality form. So we have total to warehouses must be equal to total from warehouses, and we are having these constraints in the model. Now, let's go ahead and solve the model by clicking the Optimize button on the ribbon. This time, we are going to step our way through guided mode and see what it can tell us. This feature is a guide offering help for you in each step of your modeling efforts with information to help prevent common errors. So let's click on Continue. Two things happen here. First, Solver has analyzed all the formulas in this model and determined the structure of our model automatically. This model is diagnosed as LP convex. LP stands for linear programming. Because the right solver engine wasn't selected for solving this LP model or linear programming model, it is letting us know and giving us other choices. So LSGRG is the right solver engine for solving a nonlinear type problem. It was selected by mistake. So this guided mode is letting us know that the LP, standard LP quadratic, is the right solver engine. So I'm going to choose that, the engine that is offered, and go on to next step. Now, guided mode tells us that solver found a solution, all constraints and optimality conditions are satisfied. Let's click OK. Now we are back where we were, without the guided mode. Here is the solution. We achieved what we wanted here, which was to determine how best to ship products between factories and warehouses and customers. So to minimize our shipping costs, which is now determined to be $519,700. And here in the output, you will see a report of the solution messages. You can see the solve time, engine solve time, and if you want to learn more about these messages that are in green, you just click on them and it pops up this Analytics Solver Help, and you can learn more about what this message means. Now, imagine you have used this guided mode for a while and you are solving over and over. You might want to get rid of the dialogues that you have to click through every time. To make this change, let me show you again. Click on Help, Operating Mode. You can see I've selected Guided Mode. There are two more options. Instead of going to Expert Mode, which eliminates the help, you have another choice, Auto Help Mode, that will only bring up the dialogues when there is a problem. But I'm going to keep the guided mode for our examples today. We just looked at how optimization can help us with a typical transportation problem. Next, let's look at an inventory management example. Then we can define an optimization model from scratch. Let's increase the size. This problem is about a warehouse that sells 4 products with a different demand for each product. Here you can see the demand and products 1 through 4. Each product has a different holding cost and requires a certain amount of space. We have a limited storage capacity. So, what is the best ordering policy for a warehouse to minimize costs while meeting demands? There is an analytical solution for this problem, which is known as economic order quantity, or EOQ. Unfortunately, this formula doesn't always work in the real world. Demand usually fluctuates, ordering time is variable, and other factors arise to further complicate the problem. In this model, we have one such factor, a limited storage space. So the variables are called quantities, and these are the amounts to order each month for each product. The constraint, we have this capacity constraint, space used should be less than available space, which is recorded in this cell. If the storage limit wasn't present, the solution to the problem could be calculated by the economic order quantity formula. However, given the storage limit, the solution will be less than EOQ. And then let's look at the objective. It is minimization of total cost in cell E17. So let's take a look. You can see it is calculated by adding the individual costs for each product. Let's, for example, look at one of these costs. It is calculated by using holding cost times average inventory level plus the cost to place an order times average number of orders. B13 is our decision variable, and you can see that here having the variable as a denominator changes this model from a linear structure to a nonlinear one. As you will see, the guided mode verifies this. So let's click on Optimize, click on Continue. This model was diagnosed as NLP non-convex or nonlinear programming. Next step, and we get the optimal solution. Here are the results: the amounts to order each month, minimizing cost, meeting demand, and without exceeding the storage space. Now on to our example in a financial services application, allocating money to stocks. This is about an investor who wants to target a specific rate of return for his portfolio while minimizing risk. So this is a portfolio optimization application. And the goal is to find the best combination of stocks that minimizes risk for a given return. Let's open the Excel workbook. On Premium Solver platform, you can see that no optimization model is defined under optimization, and we are going to do that together. As you can see, the returns, the variance and covariance between all stocks are known, and I have already organized the data and created the formulas on the spreadsheet. In this problem, the decision variables are the percentage allocations of the funds that we can invest in each of 5 stocks. So we need to have 5 cells. So I have stock 1 to 5 here, and I plan to use C14 through G14 to hold the percentage allocations of funds or the decision variables. And you can see that I have named this block allocations. Now we have to let solver know that these are our decision variables. So we are going to select, use mouse to select this range for decision variables on the worksheet, then click on decisions here, or you can also use the drop down and use normal. Now you can see that we can verify we have done this correctly by checking the model tab again. Under variables normal, you can see allocations, block of variables with the name allocations is added. To define the objective of our problem, first we need to create a formula on the worksheet to calculate the measure that we need to optimize. Here, this measure is portfolio variance. Then we need to tell solver whether we want to maximize or minimize our measure and where that formula is. So I have defined a quadratic function at cell C18 to calculate the portfolio variance by a custom quad product function. You can see this function. Now you can use your mouse to select this cell on the worksheet. Then click on Objective and choose Minimize to define C18 as our objective function to be minimized, or we choose min. And it has the name range portfolio variance. For this problem, we have 2 constraints. We want to make sure the total portfolio equals 100% and that its return is at least 9.5%. For the first constraint, we need to calculate the total portfolio with a sum function over the allocations. Then we need to tell solver that the sum of allocations of funds to stocks equals 100% or 1. I have used cell H14 to represent the formula of this constraint. Here, sum of all allocations. So let's use our mouse to select this cell on the worksheet, then click on Constraints button on the ribbon. Let's choose first option, Constraints. Now let's choose the equal sign to define H14 or total portfolio as our left-hand side. Now in this Add Constraint dialog, we can enter 100% or 1 for the right-hand side. So let's enter 1 and click OK. Now look at the task pane, Model tab. You can see that this constraint, total portfolio equals 1, is added. Our second constraint is total portfolio return, which must be greater than 9.5%. We need to set up one cell in the spreadsheet to represent the formula of this constraint. Here I've used cell C20 using a sum product of allocations and stock returns. So use your mouse to select this cell on the worksheet, then click on Constraint button and Constraint. Let's choose greater than or equal to. If you by mistake choose less than or equal to, it's totally fine. You can just use this drop down and change it to greater than or equal to. Now portfolio return is our left hand side, and then for our right hand side, let's enter 9.5%. Then click OK. Click and verify this is added correctly in the Model tab of Tasking. By doing this, we have defined our business problem in the optimization language for Solver. Now we are ready to hit the Solve button and get the results. Let's click on Optimize. Let's click on Continue. This problem is diagnosed as quadratic programming convex. Next step, and we get the optimal solution. So this is the allocations of funds to different stocks, resulting in the minimum risk or minimum variance portfolio that equals 100% and achieves a 9.5% return. This is often called an efficient portfolio. You may have heard of the efficient frontier. Using Premium Solver, we can construct that efficient frontier rather easily. Here I will show you how. So far, in our example, we have used Solver and found the optimal portfolio with minimum variance for a given target rate of return of 9.5%. Let's generalize that. We can utilize parametric optimization to find the efficient frontier that is the optimal solution for several levels of portfolio return. To do this, let's choose an empty cell. For example, let's use a D20. I'm going to change its color so we know where to look for it. Now, select that cell, click on Premium Solver Platform. Let's click on Parameters, Optimization to insert a parameter. This dialog box will open. We are going to define a parametric return rate, and we would like to see the optimal solution for different return values between 8 and 14%, as one of our stocks returns 14%. So let's input 8% for the lower level and 14% for the upper level. Now we have to modify our constraint right-hand side to point to our parametric return rate. So let's click OK and click on Model tab to verify that this parameter D20 is added. So let's go ahead and modify our constraint right-hand side to point to our parametric return rate instead of the constant value of 9.5% in the right-hand side. So let's double-click on this constraint and choose this button, point to D20. You can see in the right-hand side now we have the constant D20. Instead of the constant, we have D20. And click OK. Again, let's verify this has been done correctly in the Model tab. Next, we need to tell Solver that we need to run, for example, 10 optimizations so that Solver finds a solution for different levels between 8 and 14%. So let's go to TaskMain Platform tab and set the number of optimizations to 10. Okay, let's go to Output tab. Do one more thing. Let's clear this message so we can see all the 10 optimizations. And now we can click on Optimize. I'm going to skip guidance, and here are the solution. Optimization 1 through 10, all finished. The worksheet will initially display values for the last optimization with the return value of 14%. You can see the decision variables, the variance, return, but we can display any of the optimization results by changing the selection on the menu in the tools optimization number. So, for example, let's check the second optimization. Here are the results. You can see the return was 8.67% and variance is 0.44%. You can see the decision variables. Now, let's click on Charts, Multiple Optimization, Monitored Cells. Let's select the Objective Portfolio Variance and click on this button to move it to the right side. Now click OK. This is the efficient frontier plot. On the x-coordinate, we can see the optimization index. Now let's click on this right button on the right side to open the right side options, the right pane. And we can open this drop down and open the chart options. For x-coordinate, down here you can see we have two options, either the optimization number or the value of our parametric return rate for that specific optimization run. So let's choose parametric optimization. And now you can see the return threshold on the x-coordinate. Let's close this and go back to our slides for a recap on what we practiced. Modeling and solving problems in Excel spreadsheets. So you can just determine the decision variables and reserve required cells to hold the values of each variable. Then pick a cell to represent the objective function and enter a formula that calculates the objective function value in this cell. Pick other cells and use them to enter the formulas that calculate the left-hand side sides of the constraints. The constraint right-hand side can be entered as numbers in other cells or entered directly in the solver's add constraint dialog. And one quick note, it is best practice to use constants for constraint right-hand sides. Now, let's look at some scheduling examples. This example is about allocating staff. This is about an amusement park that needs a certain number of employees each day of the week. Every employee must be on a schedule that gives him or her 2 consecutive days off. How many employees should the park hire and what a schedule should they be on to minimize total payroll cost? Let me open the Excel workbook. So this is the model. So for employees working 5 consecutive days with 2 days off, we are looking to find a schedule which meets demand from attendance levels while minimizing payroll costs. Let's look at this model. We have 7 possible schedules. We call them A through G. The decision variables reflect the number of people hired for each of the 7 possible schedules. So we need to tell solver that the solutions need to be integer values, whole numbers such as 2, 3, or 5 people. To do this, you need to select your variables. So first, let's define this as our variables. So select the whole block and click on decision. You can see employee per schedule, which is the name of this block, is added. It was already added. But let's practice and we're going to delete that together. So then we want to tell solver that these needs to be integer or whole numbers. So select the block and click on constraints, variable type bound, and you can see integer is here. So just select that. So let's get rid of one of these variable blocks because we have defined the variables 2 times and this will give us an error. So you can right click and click on delete. Same with integer, you can right click and select delete. Here the constraint is total demand or required number of people. However, we also need to tell solver that the variables need to take positive values. There are 2 ways to do this. You can select the variables and then click on constraints, variable type bound, and then choose greater than or equal to, and then give a lower bound of 0, and then click OK. So this is the way to make sure that we get positive values for our number of employees that are required. We don't get negative values. However, since this is a common occurrence, there is a shortcut. Let me show you. Click on Engine tab of the task pane. You can see that we have Assume non-negative. And you can set this to true or false, and this is set to true. And it's only set for this problem. So let's go back and delete this lower bound on our decision variables because we already told solver that assume non-negative for all variables. So let's delete this. And then our objective is to minimize our total payroll, which is calculated in cell D20. Okay, let's solve this problem. Click on Optimize, and I'm going to skip guidance, and here are the results. The number of required people for each schedule. Now, the next workbook is another version of this problem. Let's take a look. I'm going to increase the size. So the park has hired the required employees. It now needs to decide which employee goes on which schedule. Each employee has given a list with his or her preferences. So here's the list. So we have employee 1 to 25, and then we have schedules A through G. A 7 means most desired schedule, and 1 means the least desired. How should the park divide the schedules among the employees to maximize the preferences? So we have to define 7 decision variables for each of 7 schedules per employee. Then decide to allocate only one of the schedules to each employee. Whether to allocate a schedule to an employee is a yes-no decision. We have an easy way to do this in optimization modeling. We can define the variables as binary, meaning the variable can only take 0 or 1 values. So if one of the variables here in cell, for example, A under schedule A, M24 gets 1, takes a value of 1, it means that employee number 1 is assigned to schedule A. To define cells as binary, let me show you that. So let's go to Model tab. You can see this whole block is defined as schedules. After defining your variables, select the whole block. For those ones that need to be defined as binary, go to Constraints, Variable Type Down, and then define binary. And you can see this was already defined, so let's get rid of one of them. So this schedule needs to take values 1 or 0. Now, we need to tell Solver that each employee can be allocated to only one schedule. So we need to define a sum function over all the variables related to each employee. We have this block of 7 variables per employee. Employee 1, employee 2. So we have this sum for each of the variables. You can see it is defined for each of the employees. And then we need to define a constraint and make all these sums equal to 1. So you can select the whole block. We need to do this one by one, define the whole block and click on constraint and then equal to 1. Click OK. And you can see that it was already defined, so I'm going to get rid of one of them. Schedule per employee equals 1. Then the employee schedule have to be equal to the required employee. So we need to sum all the variables that are under one schedule. This way, calculate the total number of employees within that schedule. Then we can define this constraint. So look here, we have the sum over each schedule in this row. We have the totals, number of people for each of the schedules, and then we have the demand here. And you can see that employee schedule equals employee required. The objective is to optimize employee preferences, and in this case, that means maximizing the sum of the preferences over all the employees. Let's look at this function. So total preferences need to be maximized, and this is defined in U50. You can see it is highlighted. Let's take a look. So we have defined this sum over all the employees. Let's take a look at one of them. We have used this, for example, for employee number 1. We have this sum product function to multiply the array of variables by the array of input express preferences. For example, for employee 1, if we're sure he is allocated to schedule A, we have one variable under A. You can see it is 1. That takes value of 1. All other will take 0. We call that only one schedule will be assigned to each employee. And then since the express preference for schedule A is 4, the sum product returns 4. And this value contributes to our objective. You can see the total in U50 is 4. So this is how we calculate total preferences for all the employees. Now let's get ready. Let's click on, we are ready. Let's click on optimize. And I'm going to skip, let's click on continue actually. Let me show you that this model is diagnosed as LP-MIP. It means linear programming, mixed integer programming. And the reason it's mixed integer programming because we have integer or binary variables. And let's skip guidance and get the results. You can see all of the variables take values of 0s or 1. And we only have one value of 1 in for each employee, meaning that employee is assigned to only one schedule. In this model, we solve the problem after finding the optimal solution of scheduling 1. It is also possible to find both solutions automatically. You can write a VBA macro to do this. So it is a good time to talk briefly about automating your models. This allows you to run your predefined optimization models and control the solver. You can automatically update data, run the model and retrieve the results, and also create an application to distribute to your end users. You can automate your models and control solver engines using VBA Object-Oriented API. Let's quickly look at a VBA code that shows one of the many ways you can use the object-oriented API, such as how to call the solver to solve the problem and how to retrieve sensitivity information from the VBA. This example is about an oil refinery that purchases 2 crude oils, and then these crude oils are put through 4 processes: distillation, reforming, cracking, and blending, to produce petrols and fuels, which are then sold. And the problem is to the goal in this problem is to plan the operations of the refinery to maximize total profit. And if you look, you can see that decision variables and constraints, objective functions are all defined. Now let's take a look at the code. Let's click on Developer, Visual Basic. Just going to point you briefly on main points. Within prob as new problem, you define a new instance of a problem. Create an instance of the problem. Here you can go to select an engine, turn off guided mode, set the parameters, but with prop.solver.optimize, we run the optimization. It's like clicking on that optimize button on the ribbon. And then in this next line, you're putting message boxes. Main thing is that how we are getting the decision variable values, dual values, we call them reduce cost shadow prices in these message boxes and for loops. And then finally, you can see we have prop.solver report, and we are asking for an answer report, and you will see that happen when we run this. Let's close this. Going to click on this button. We get the optimization status, which is problem is optimized, and then we get final variable values. And if I click through this, you get to see the reduced costs, shadow prices, and finally we get the answer report generated for us as we requested. Now, let's briefly talk about our product line. You can access our optimization software within Analytics Solver Platform or Risk Solver Platform products, or get it as a standalone program such as Premium Solver Platform or even Premium Solver Pro. Everything that we saw today can be done using Premium Solver Pro or more advanced products, subject to your model size. The Solver Upgrade products have very nice usability features with limits related to your problem size, structure, and solver engines. The platform products allow you to add 8 different larger-scale plugin solver engines that you can use to extend the power of these products, such as Gurobi, Nitro, so on. These make it practical to solve very large problems, essentially only limited by memory. But you can do much more with our products. We offer a complete solution for any type of conventional and stochastic optimization problems, simulation and risk analysis, decision trees, and forecasting and data mining. You can find optimal solutions for models with uncertainty using chance constraints, recourse decision variables, and robust optimization and stochastic programming methods. This wide-ranging product line empowers you to perform analytics on the web and desktop spreadsheets, also web server and desktop applications in any scale. As we mentioned earlier, many of our customers have found optimal solutions for their industrial problems worth millions in savings. We saw today how building a model can give you insights as well as a money-saving optimal solution. Frontline Solvers offers powerful tools to help you get a better solution by automatically diagnosing model structure, fixing problems for you, selecting the right solver engine, and providing updated information at each step. For instance, one of these features, the guided mode, helped us choose the right engine. If you are wondering what is the next best step to begin, please register at our website for free. This allows you to access our downloadable user guide, more than 40 example models like the ones we have been showing here. Furthermore, it allows you to download a free trial anytime you are ready. try it yourself. After installation, let me show you how you can go to example models. But during this trial period, you have full technical support. You can ask questions. Just give us a call. Use this special number for this webinar attendees. Use live chat or send us an email. I'm going to share my email address. It is consulting@solver.com. So consulting@solver.com. You're welcome to send any questions or comments to my email. Now let me show you how you can access user guides and examples after you install the trial. So just click on Help and then click on Examples. This new workbook will open. This allows you to access any of optimization, simulation, and data mining databases. For example, we have the optimization examples here, some explanation of the problem. For accessing the examples I reviewed with you today, you can see there's a line 19 here, and click on optimization there, and here you can find the examples that I reviewed to do. For example, click on logistic examples, and transport tree was the example we reviewed about transportation operation today. So all of them are available here. And also you can see the VBA examples, the refinery model that we'll take a look, and then the cutting stack, which is an optimization model from scratch defined in VBA. Furthermore, other resources that are available to you, click on Help and click on User Guide. The third one is the main user guide. We have the engine guide if you want to learn more about engine options that are available for each of the solver engines. But click on your main user guide, and here it's a PDF, and then you can see that how to define your optimization model from scratch, and then there are chapters on automating optimization in VBA. This is more advanced stuff, but if you one day decide to automate your optimization model, this is available to you. And then mastering conventional optimization concept, this is very helpful if you're starting to build larger scale models, very useful information. And then another chapter I highly recommend you take a look before building larger scale models is this chapter, starting page 402, very helpful, helps you to prevent some errors that later impact your performance of your model. For example, using Excel functions like if, lookups that make your models non-smooth, and then it's really hard to solve those you can't solve those kind of problems. It is hard because you cannot get a proven optimal solutions that you can get in a convex linear or nonlinear problem types. So very helpful information here for you. Another resource that is available to you is our YouTube channel. And we update videos here, the very recent YouTube knowledge solvers, and click on playlists, and you can get some videos on how to use this free solver app for Google Sheets, Excel Online. You can see the webinar recordings. There are videos available on stochastic optimization, other products that are available. If you're joining us tomorrow on simulation and risk analysis, there's some more videos, and on Thursday we talk about data mining, Solver SDK, and so on. So these are other resources available to you. Another free, very good resource that is made available is our optimization course, and we just updated all the videos, and this is the link. You can see my colleague Bob, I just shared the link with you, solver.com training optimization introduction course. So this is a 3-module course with training videos, more in-depth information. For example, if you want to learn about structure of optimization problems, what it means if it's linear, non-linear, non-smooth, what the engines do to find solutions, they're all available in the course. Different types of optimization problems that gives you a very broad understanding of these type of problems. If you are new to this area, if you want to learn more about our product, so it applies for really all of these groups. And then in the third session in the third module, we have videos on developing optimization models from scratch using VBA and also using our Solver SDK platform. So these are all available to you at no charge. Please use them, and Again, you're welcome to send any questions or comments to my email address, consulting@solver.com. Let me now go to your questions. So Kenneth is asking, do we support nonlinear mixed integer programming problems? Yes, we support nonlinear mixed integer problems. Yes, that is correct. You can define nonlinear problems that are mixed integer. If you have any other questions, please type them to the chat box, or feel free to practice, come up with questions, use my email address, use the online chat. We look forward to future webinars with you. We appreciate your time, and I look forward to seeing those of you who are interested in simulation and simulation optimization for webinar tomorrow at the same time. And if you're interested to learn about our data mining and how to access big data using our Excel Miner platform, you're welcome to join us on Thursday at 9 a.m. Pacific time. Have a great rest of the day. Thank you again. Until next time. Bye for now.